All right, so this is recording. So again, if you don't want to be in the recording, just keep your camera off. So stuff that's important for this test, really the test is just going to be on 11.1 through 11.6. Okay. And then 11.7, I think, is a great way to review. 11.7 is just a review of these previous sections, and it's mostly focused on just the series stuff. Okay, so whether series converge or diverge. So I think the problems here are good because they're very similar to what you're going to see on the tests. They will give you a series and then just ask you if it's convergent or divergent. They don't tell you what kind of series it is or what kind of test to use, and that's pretty much what you're going to see on the test. I will say the problems in this, they don't ask about absolute convergence or conditional convergence explicitly. So I would also throw in some problems from 11.6 for that absolute convergence and conditional convergence. Okay, so in order to get those concepts. And then also, I would also, so these two sections are very important. I would also loop back to sections 11.1 and 11.2 because 11.1 is really the only section we deal explicitly with sequences. And then 11.2 is the only time we talk about what the sums of these series are. So in the other sections, they don't ask you to find the sums, but we still need to know how to do that. Remember, there's only two types of series we find sums for in this course, the geometric series and the telescoping series. Okay. So real quick, I think 11.1 will be, it's fairly straightforward, so I'm not going to review that too much. Just know the basic techniques for finding a limit of a sequence. I probably won't even ask any questions on the tests about finding limits of sequences or anything. I'm probably just going to focus on the series. But 11.2, let's look at these geometric and tell us these sums of geometric series. So one thing is that for the geometric series, okay, so that's something like this. A series like this where a is a constant, then we have r to these increasing powers of n. But the formula we have for a sum of the geometric series, it kind of depends on this specific form of the series. Okay, so we have starting at 1 and to r to the power of n minus 1. So when we have a series like that, we have a nice formula for the sum, and it's a over 1 minus r. Okay, I would review or investigate how to find the sum of something like this. Okay, what if we have, instead of r minus 1, what if we have r to the n? Okay, how does that affect the series? So there's a couple ways to approach this. You could pull out an r from here to get this in the form we like. Okay, so this is the same as a times r to the n minus 1, right? Okay, so now I can use my formula where I'll pretend this is my a and then this is my r to the n minus 1. So the sum of this series would be something like that. And then there's a couple ways to approach this, but I think this is a useful concept to know. Okay, so any questions on that front? No? All right. Telescoping series, as far as the sums of telescoping series go, I'm probably not going to give you any kind of crazy. There's some telescoping series that you can't really tell are telescoping series, like maybe something like this. This is a telescoping series, but you can't tell until you use partial fractions to rewrite this into a telescoping series. So I'm probably not going to give you anything like that. If I give you a telescoping series, you should be able to tell. If you guys know what the definition of a telescoping series is, I'm probably going to give you something more like something more like this, where it's obvious right away it's a telescoping series. All right. So I'm not going to give you any tricky ones that are this form. If I give you any telescoping series, it's probably going to be more like this. All right. Any questions on that? No? All right. As far as I'll kind of go through it, kind of give a quick rundown section by section before I do problems of notes I want to make clear to you guys. So 11.3 is about integral test. So for integral test, okay, we have a series. And if I look at the series and I see the stuff inside the series is something I could integrate, you know, that is a good clue for integral test. So let's say I have like n e to the negative n squared or something. This is something I could use integral test on. So what do? I turn this into an integral, an improper integral, 1 to x, or excuse me, 1 to t. Well, really, let's see. At first, it should be 1 to infinity, right? That's how I start my improper integral. Okay. So I write it as an improper integral. And then remember your tools from 7-8 when we were working on improper integrals. The next step is really critical, where you have to do your improper integral correctly, where remember you have to write it as a limit and replace that infinity with that t. Okay. If you just solve the integral 1 to infinity and plug infinity into your bounds and don't turn it into a limit, you're gonna lose points. Okay, so make sure you write it as a limit and do the improper integral in the correct way, writing it as a limit and then evaluating the limit at the end. 11.4, comparison test. So comparison test, really tricky for a lot of people. The inequalities screw a lot of people up. Just remember that we have to, I'll go over more when we work the problems on what we need to write for each problem. But remember, big picture, okay? I need everything greater than or equal to 0, right? I need all these to be greater than or equal to 0 and all these to be greater than or equal to 0 to use comparison test. And comparison test, I have to be careful on when I use it, okay? If this series is divergent, if this is my original series, I'm comparing it to Bn, and Bn is divergent, okay? This comparison doesn't tell me anything, okay? On the other hand, if this is my original series and Bn is convergent, okay, then I know An is convergent. All right, so you got to know when the comparison test actually can be applied and when it's garbage, when it's not telling you anything. Okay, So if Bn is divergent and An is less than or equal to Bn, we know nothing. Okay. On the other hand, if Bn is convergent, then we know An is convergent. All right. And then on the other hand, let's say Bn is my original series, and I'm comparing it to An. Okay. If An is convergent, again, I don't know anything. On the other hand, if An is divergent, then I know Bn is divergent. Okay. So any questions? All right. Oh, let's see, chat. Yeah, I'll talk about how many questions are on the test in each section in a little bit. Probably before I start working on problems, I'll kind of go over that. Okay, alternating series tests. I want you guys to remember, let's see, we use alternating series tests to figure out if something's convergent, but remember, we don't want to say divergent by alternating series tests. Okay. We should only say something is convergent by alternating series test. If we're looking at an alternating series and it looks like it's going to be divergent, we're usually going to say divergent by divergence test. All right. Any questions there? Is everybody familiar with that? All right. Okay, so 11.6 is kind of the last section of new material. So for 11.6, okay, if you want to look at my notes or look at my video for 11.6, I think it's pretty clear what I want from there. Let's see, we're talking about absolute convergence. Boom. Absolute convergence. So there's a couple ways we can tell if something's absolutely convergent. Okay, so one is what I called in my notes and in my video the direct approach. This is my terminology. It's not, official. Okay, so remember what absolute convergence means. If I have a series AN, okay, maybe there's some negative terms in there. Maybe it's an alternating series. It doesn't have to be. Maybe it's all positive. But if we want to see if this is absolutely convergent, what am I going to do? I'm going to look at the series of absolute values. So I'm just going to take the absolute values of all the terms. And then I'm going to look at this series. And if this series is convergent, then I say my original series is absolutely convergent. Okay. So this direct approach, what am I going to do? I'm going to start with my original series, and then I'm just going to look at the absolute values and see if that series converges. So an example of what I mean is maybe I have this, it's an alternating series, okay? And instead of looking at these negative terms, I'm going to take the absolute value of everything, and these aren't equal, okay? When I do the absolute values of everything, these two series aren't equal. Okay, and then I look at this series of absolute values, okay? And then I can use all my previous tests from sections 11.2 to 11.5, right? I could say that this is convergent by p-test, okay? So I can use all my old material to look at this series of absolute values. Okay, so I just look at the series of absolute values and I see it's convergent. So that means my original series is absolutely convergent. All right, so this is what I call the direct approach. We just turn it into absolute values and look at that series directly. Then the other two ways to tell if something's absolutely convergent are ratio test and root test. Okay, so those are very powerful tests. They're pretty straightforward, right? It's, once you've done a couple, maybe you see how they work. We got to be careful though, because these, if we want to show something's conditionally convergent, we got to do some extra stuff. These never show conditionally convergent. So we should never say anything like conditionally convergent by ratio test. Okay. These only show if something is absolutely convergent or divergent. All right. Any questions there? All right. So how do we show conditional I had, several questions this week on how do we actually show something is conditionally convergent. Okay, remember, we got to do two things, and it doesn't really matter what order we do them in, okay? I have to show the series of absolute values is divergent. And then I have to show the original series is convergent. Okay, so I need to show these two things separately. And again, if I'm showing something's conditionally convergent, I don't want to use ratio test and root test, all right? So for this one, maybe I use this direct approach that I was talking about where I turn everything into absolute values. And then I use my old material, like my integral test, my p-test, things like that to show this is divergent. And then for 2, showing that this original series is convergent, maybe I have to use alternating series tests. That's going to be very common for alternating series to be conditionally convergent. That's usually where you'll see it. That's not the only place, but so keep an eye on that. Any questions? All right. So that's pretty much it as far as the overview of the material. In my opinion, I think this test is kind of narrow. It's just about really 11.2 through 11.6 with a little bit of 11.1. In previous semesters, there was, a couple extra sections, but we'll just put that on the final. Now let's talk about what I want to, about the test itself. Okay, so Tim asked how many questions in each section. So I'm probably gonna do more questions in the multiple choice section, maybe as many as 10 in the multiple choice. Okay, they're not all gonna be problems that you have to work through to find the answer. Maybe some of them will be like short concept questions, like true, false. Like I'll give you a statement, just a general statement about series, like, okay, if I have a P series and P is greater than 1, the series is convergent, true or false. All right. So maybe a few like that. And then there will be some problems you actually have to solve out by hand to find the answer and then choose the correct answer. Okay. So about 10 of those multiple choice questions, some being just concept and some being problems. And then I'll probably do fewer of the upload questions. Okay, so maybe like 4 or 5 questions where you have to write out the answer by hand like you would on a normal in-class exam. So I'd say like 5 of the normal questions to upload. I'll adjust that at like once I have my test written out, I'll take the test like I do normally for your in-class exams and see how long it takes me to do it. And then I will adjust accordingly. I based on how long it takes me to write out the answers of the test, I know how long it'll take you guys approximately. My goal is to have it be pretty much the same length as an in-class exam. Ideally you should be able to do it in one of our normal class periods, like 2 hours. And then I'm going to give you another 2 hours. You're going to have 4 hours total just to account for like internet issues and uploading and all that. So I think you guys will have plenty of time on that front. The test I'm designing should only take 2 hours. Any questions on format or time or anything like that? I said not to use ratio test or root test for conditional convergence. You can use p-test, but don't use ratio test, root test for. Okay. Yeah, and in fact, for conditional convergence, yeah, you might very well use p-series in showing something's conditionally convergent. So, just a quick example of what I mean by that. For example, if I had this series, -1 to the n, 1 over n to the power of 0.9. Okay, this is going to be conditionally convergent. So what would I do? Okay, remember my steps. I got to show the absolute values are divergent. So when I do absolute values, I get this series. Okay, now this is a p series and p is less than 1, right? So I say, okay, this is divergent by p-test. So I'm going to use the p-test here. And then step 2 is showing the original series is convergent. Okay, so this thing, my original, is convergent by alternating series test, right? And I need to show all the steps for alternating series test, but that's how I would do that one, convergent by alternating series test. So yeah, you might use p-test in conditional convergence. All right, any further questions? Okay. So now, before I do problems, just a kind of quick note on what I want to see from you guys when you're answering the upload portion. Okay, so just some of you uploaded work for your multiple choice questions in your upload portion. And, it's not a big deal, but on the test, just to make, the files smaller and it easier for me to read, only upload your work for the upload portion. Okay, it'll just make my life easier. So just don't show me the work for the multiple choice section. I don't need to see it. I don't want to see it. I'm only going to grade the upload portion. So only show me that work. Okay, but now let's see what kind of work you need. The main thing is you got to show all your steps. You got to check all conditions for whatever test you're using, and you have to specifically name whatever test you're using. Okay, so now I'll kind of show you guys what I mean by just working some problems. Okay, this is a good one. Okay, so let's check this problem. This is again one from 11.7, so I think 11.7 is full of good problems. Let's see. So how would we work this? Let's see. Think about sign. Depending on n, sign could be positive or negative. Okay, it's not going to be an alternating series. It's not going to be every other term is positive or negative. Maybe several in a row will be positive, and then you have a negative. But there's negatives in there, so that might screw me up. So I should probably try and show this is absolutely convergent. Okay. Okay, so this is what I'm trying to show. All right, so what do I have for absolute convergence? I have my several methods. I got my ratio test, root test, and my kind of direct approach. One thing I'll say about absolute convergence with trig stuff, you usually don't want to do ratio test or root test because if I do ratio test on this one, okay, I'm going to end up with sine of 2n plus 2 over sine of 2n, and then trying to figure out what that ratio is, the limit of that ratio is, and then I'm going to have some other stuff. The problem is I can't really figure out what ratio of the trig stuff is going to be. It's going to be constantly changing since sine is oscillating forever. So you're never really going to be able to figure out what that limit is. So usually on the trig stuff for absolute convergence, you want to use that kind of direct approach where you take the absolute values and try and show it's convergent directly. Okay, so if I take the absolute value of the stuff, let's see. Maybe it doesn't seem helpful at first, but since sine is always less than 1, we can say this is less than or equal to 1 over 1 plus 2n, right? And then this thing is less than or equal to just 1 over 2 to the n, right? I'm doing comparison, you know, I'm comparing this series to 1 over 2 to the n. Okay, so now you know, I should be considering all these as series. Okay. So what do I know about this series? This is a convergent P series, right? So that's telling me, okay, this is going to be convergent. And so my series is going to be absolutely continuous. So it's continuous. All right, so how would I write up this answer? This is kind of my like scratch work. How do I want you guys to write it up? I would say, okay, if I was going to write this out formally, I'd be like, boom. Oh, you know what? Yeah. I'm actually going to have my series AN is going to be the sine, absolute value of sine of 2n. And I'll say my series Bn is 1 over 2 to the n. I will say, let's see, An and Bn, I need to check my conditions for comparison tests. Excuse me, I'm trying to admit somebody. Okay. So I want to show, let's see, I need to say An and Bn are greater than or equal to 0 for all n. That's, you know, clear. We got absolute values here, so that's always going to be greater than 0, and it's obviously greater than 0 here. So we say this, boom, and then, you know, I have my inequality here, and I said maybe I need to make that clear. I say An is less than or equal to Bn for all n. Okay, so I have my conditions for comparison tests. Boom. I would say something like series Bn converges by p-test, or wait, not p-test, geometric series test. So series An convergent by comparison test. I apologize for my handwriting. Hopefully you guys can tell as I'm talking what I'm writing. Okay, so converges by comparison test. Okay, and then what do I need to write? I can say, all right, I can say something like original series is thus absolutely convergent. So it's convergent. Okay, so this is kind of how want you guys to answer. And I know there's a lot of writing, and maybe you guys aren't used to writing so much for math problems, like, actual words, but the higher you go in math, the more you're going to have to do that. My work looks like essays. There's barely any, equations in it. So get used to writing out sentences like this. You have your scratch work or your work where you're showing your inequalities and so on, but then we really need these sentences. Okay, so I really need this sentence that, okay, the series Bn converges by geometric series test. I have to state this, why this series Bn converges. Okay, yeah, maybe it's clear to you from here that this series converges, 1 over 2 to the n converges, but I have to say why it converges by geometric series test. Okay. And then I need to say why an converges, this series of absolute values. It's by comparison test, right? I need to say by comparison test. And then finally, all right, what's my conclusion? This series of absolute values converges. So my original series is absolutely convergent. And so it is convergent, because absolutely convergent implies convergent. All right, any questions? I know that was a lot, but everybody good? All right. So that's kind of an example of what I would want you to see and kind of the amount you have to write for that one. Now let's just do some more. Okay, this is a good one that's maybe using a technique you guys don't use very much. Okay, so this is about just by properties of geometric, or not geometric series, but series in general. Remember, if I have two, let's say I have two series AN, I have a series AN and a series BN that are both convergent, then I can add these series together to this one series AN and BN. Okay. All right. And it can work in reverse as long as these ANs and BNs are both convergent. Okay. So looking at this one series, this is my original series, right? I know 1 over n cubed is convergent by p-test, and I know 1 over 3 to the n is a convergent geometric series. So I can split this up into 2 separate series. So how would I solve this problem? Again, how would I do it? I would say, this is convergent by p-test. And if you want to say p, because p is equal to 3 greater than 1, just to be specific of what you mean, that's fine. Okay. And then I would say 3 to the n is convergent geometric series. And again, you could say, why is it a convergent geometric series? Because r is less than 1, or absolute value of r. So and why is this true? You could just say by properties of series. If you say something like that, I'll know you mean the fact that we can split up 2 convergent series. Okay. So any questions on that? Okay, and let's see, actually, if we turn to section 11.2, maybe that has a specific name. No, it doesn't. It's just Theorem 8 in section 11.2, so no specific name. I would just say by properties of series, or by properties of convergent series if you want. Let's try. Okay, I made a review video or a problem video that's on web courses as well. It's just me working through several problems of 11.7. So after this, check that out. I think it's if you want, if you feel like you need the help or need the study. I've gone through the first 10 problems, 11.7 so far. I'll do a couple now because I think, they get progressively harder. So let's do some of those early ones. A good one, I remember, let's see. Oh yeah, this is a good one. Okay, so instructions on this problem are just determine whether the series is convergent or divergent. Okay, so I have numerator to a power of n and denominator to a power of n. Okay, and they're different powers of n, but since n is in both of these exponents, that makes me think root test. Okay, so root test, I can try and use it to show something's convergent. Okay, if I show something's absolutely convergent, then it's convergent, right? So if I use root test, this should tell me that this series is absolutely convergent, which will mean it's convergent. All right. So how would I want that written out? Okay, so this is the problem. Okay, maybe write something like, all right, an is your stuff inside the series, or we should be taking the nth root of absolute value of an, right? So I'll say, there's no negatives here, but I can be clear. I can say absolute value of an is this stuff inside the series. And then nth root of an. Okay, what do I get when I take the nth root of this? All right, the n should cancel, right? And I should be left with n squared over 1 plus n squared. Or no, 1 plus n cubed, excuse me. Okay, and then what's the limit? This is what I need for root test, right? If I take the limit of this, okay, so this is my nth root of an, absolute value of an. If I take the limit of this, I got power of 2 on top. And then if I expanded all this on the denominator, I'd have n cubed plus blah, 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 right? So I got a higher power on the bottom. So this is maybe where some skills from 11.1 come in. What's the limit of that? I got a higher power on the bottom, so the limit should be 0. Okay. How do I wrap all this up? I need to state explicitly what the root test tells me. I would say limit of nth root of an equals 0. So series absolutely convergent by root test. So it's convergent. All right. So really, hopefully I'm hammering home that really this kind of conclusion sentence is important. All right. We really have to wrap up and really state explicitly. It's not just enough. So for example, let's say we didn't have any of this. Let's say we just had this from maybe maybe I just had from that line up, and then maybe I wrote, convergent, because at this point you can tell it's convergent, right? Okay, so maybe you just had your work here, you showed the nth root, the limit goes to 0, and you said, okay, well, that means it's convergent. You would lose a lot of points, okay? Even though, this is all correct, we really need to be specific. So that's something that I think goes beyond just notation error, all right? It's really critical. And especially if I'm not grading the final, you'd lose like all your points on the final if somebody else is just grading. So really, really critical to have something like this. All right, I need to say my series is absolutely convergent by root test, so it's convergent. Any questions? All right. All right. So I have said all the stuff I want that I think is critical importance. I will stay online and keep working. If anybody has questions, if you're here just for the STEM seminar credit, what I'm going to do is I'm going to type attendance in the chat and just say type here in the chat before you sign off, and I'll give you credit for the attendance. I'll give you a couple minutes. So if you're going to sign off, go ahead and sign off. And then if you guys have specific questions, please let me know. Oh, you're welcome. Glad you're here. Of course, yeah. And like I said, I'm going to be doing more review. I'll continue doing review now. I'm going to do another review session tomorrow night, 6 to 7 and beyond if you guys want. And I'll continue uploading problem videos. I'll probably put another one up later tonight. No, I'll probably do some different problems. Maybe I'll kind of give the same instructions for those who tune in tomorrow that weren't here today, but I'll do different problems probably. As far as question weight, I'm thinking probably 50-50 between the multiple choice section and the upload section. So there's going to be more multiple choice section questions. Okay, so there's probably going to be like 10 multiple choice questions, and those will count probably the same as the 4 or 5 upload questions. Okay, because I mean, really the upload stuff is where I really see if you're doing things correctly. So that's kind of more important in my opinion. Of course. Uh, 11.8. Oh yeah, that's another thing I wanted. I pushed 11.8 back. 11.8 is due. Let's see, next Tuesday, I believe I said it to be due. So now, now that test 3 is this weekend, the schedule's pretty obvious to me what it should be. So I changed all the due dates of the homeworks, and those should be the final due dates. They shouldn't change anymore. So yeah, 11.8 will be due Tuesday after the test, and then, but it's not going to be every Sunday from now on. It's going to be like every 3 days or something like that, just because there's so little time left in the semester. So stay on, don't assume it's all going to be on Sundays. Check the due dates and just keep up with it, like one every 3 days. And I'll make sure the video's up for 11.8 in the next few days. You should have time to just watch it after the test if you don't want to stress about it before the test and get the homework done. Okay. So any other questions about tests or homeworks or due dates or anything like that? All right. So I will do more problems. Okay. So like I said, 11.7 is good, but it doesn't really ask about it doesn't ask about absolute convergence and conditional convergence explicitly. So let's go back to 11.6 and do some of those questions. So this, no, I won't give you the instruction. So the determine is the instructions for these are just to determine whether, let's say this one is just whether it's convergent or divergent. We could actually modify this and just ask if it's absolutely convergent, conditionally convergent, or divergent. Okay. So when you get a question like that, that's whether it's absolutely convergent or conditionally convergent or divergent. What I would try, the method I would use to approach those is try one of those tests that tell us absolute convergence, ratio test or root test. Okay. And then remember that in those tests, we have the condition that if the limit's equal to 1, it's inconclusive. That's usually when things are going to be conditionally convergent. I would say like 99% of the time, it's hard for me to think of an example you guys would see where that's not the case. Okay. So what I would do is I would do ratio test or root test on this. And okay, if the limit's less than 1, great, it's absolutely convergent. If the limit's greater than 1, it's going to be divergent. And if the limit's equal to 1, then I know I need to go through my steps to try and show it's conditionally convergent. Okay. So looking at this, I'm going to try, the first thing I would do is try ratio test. Okay. So ratio test. Okay. I need to figure out what this is first of all. Okay. And then I need to take its limit. So I would say this is equal to, let's write our an plus 1. Okay, and then I need to divide by an, which is the same as multiplying by the reciprocal, right? So when I multiply by the reciprocal, I get okay. Now I need to simplify, and the easiest way to do that is just get the similar stuff, in fractions together. So I got 3n plus 1 over 3n. I want to write those together as a fraction. Okay, I got 2 to the n plus 1, so I'll write that as a fraction. And let's see, I got n cubed, n plus 1 cubed. Okay. Now simplify. Okay, this becomes 3. This becomes 2 over 1/2, so 3 over 2. And then I got n cubed over n plus 1 cubed. All right, so this is my simplified form of an plus 1 over an. Now, remember, for ratio test, I want to figure out what the limit of that is, right? So I say, okay, if I'm taking the limit of this, I got a constant out front. I can bring the constant out. And then what's the limit of this thing? I got n cubed over n plus 1 cubed. Now, if I multiplied all this n plus 1 cubed out, I would get n cubed plus some other stuff of lower order, right? So I got n cubed over n cubed, blah, blah, blah. So the limit of that's going to be 1. So that limit's equal to 3/2 times 1, so 3/2. Okay, so I did ratio test and my limit's greater than 1. What does that tell me? My series is divergent. Okay, so how do I wrap up? I say limit an plus 1 over an equals 3/2, and I can say greater than 1. So series divergent by ratio test. Okay, any questions? All right. This is a good one. Okay, so instructions for this one: use any test to determine whether it's absolutely convergent, conditionally convergent, or divergent. So yeah, the same approach I would use last time. I want to, if my get instructions like absolutely convergent, conditionally convergent, I'm going to use one of my tests, my ratio test or root test first to see if it's absolutely convergent. And then if I get some kind of inconclusive case, then that tells me I need to, maybe go a bit deeper and see if it's conditionally convergent. So I'm going to start out by trying ratio tests. Okay. So what's an plus 1 over an? Ratio test is definitely the much more common one to use. Root test, I really only use if I see those powers of n on everything. There's a power of n here, but there's no power of n there. So I'm going to try ratio test first. Okay, if I do, remember absolute values mean I can ignore any kind of negatives, alternating sign things. So let's see, an plus 1 over an. I'll kind of maybe go quickly. That would give me ln of n over ln of n plus 1, right? And then I would need to figure out what the limit of that is. Okay, so maybe this is a difficult part for this one. What is the limit of this? Well, maybe I can't tell right away what this is, but if I turn these into functions of x, I could use L'Hopital's, right? So if these were functions of x, I'll do some work off to the side here. ln of x over ln x plus 1. Okay, I do L'Hopital's, and this will become, take the derivatives of everything, it'll become 1 over x over, okay. So the limit of this is equal to this limit. Okay, so what's this limit? Maybe now it's more clear. This limit's equal to 1. So this limit's equal to 1. So the limit of my an plus 1 over an is equal to 1. Okay, so this is some scratch work. So this is my inconclusive case, right? So that's telling me I need to check for conditional convergence. Okay, so first, let's see, what do I need to show? I need to show the absolute values, the series of absolute values are divergent. Okay, so what's the series of absolute values? Just 1 over ln of n. Okay. 1 over ln of n, let's see, ln of n is less than n, is always less than n for n greater than or equal to 2. Okay. So I know that just by knowing what the graphs look like. Okay. So maybe that wouldn't be clear right away. But if we're going to show something's divergent, usually I want to compare it to the harmonic series 1 over n, or maybe some divergent p series, something like that, like n to the power of 1/2, something like that. So I know from experience I should compare this to 1 over n. Oh, and actually the inequality is going the other way. I'm dividing by a smaller number over here, right? Because ln of n is less than or equal to n. So if I have 1 over ln of n, that should be greater than or equal to 1 over n. Okay. So I know this series is divergent by comparison. Okay. And then what about my original series? Well, that's a convergent. Convergent alternating series. But before I go into that, maybe I should, be thorough and let's see, do my conditions for comparison test. Let's see, conditions for comparison test. I would say 1 over ln of n is greater than or equal to 0 for n greater than or equal to 2, and then 1 over n greater than or equal to 0 for all n, and 1 over ln of n greater than or equal to 1 over n for n greater than or equal to 2. All right, so that's all my conditions for the comparison test. So maybe I want to continue my work on that and say, okay, so 1 over ln n divergent by comparison test. Okay, so that's part 1. I've shown the series of absolute values is divergent. Part 2, I need to show my original series, -1 to the power n, 1 over ln of n. I need to show that's a convergent alternating series. So what are my conditions for alternating series? Let's see, I need the numerical part. I need an plus 1 less than or equal to an, and I need limit an equals 0. Okay, so those are the 2 things. Okay, so really there's not much to do here. I would say 1 over ln of n plus 1 is less than or equal to 1 over ln of n. You could say for n greater than or equal to 1 or 2, whatever. Okay, so that, boom, good. So this is this one. And I would say limit. This is true, just, limit of, if I just had ln of n by itself, that goes to infinity, right? So 1 over that goes to 0. All right, boom. All right, now I need to wrap up. All right, this is my important conclusion sentence. I would say, we could just use this symbolic series. The absolute value of an is divergent by, you said by comparison test, right? And series an convergent by alternating series test. I'll abbreviate, you guys should write it out. So the series an is conditionally convergent. Any questions? All right. Let's see, so we did a divergent one, we did a conditionally convergent one. How about absolutely convergent? I hope all you guys are good on the factorial stuff. So let's do, can you go back to the first of the 3 slides for this problem? Yeah. It's that one, right? Yeah. Any question on that, Zach? Okay. And again, this is being recorded, so if you want to check the playback later, it'll be available. I'll make it available. So yeah, hopefully you guys are good on the simplifying factorials. That's definitely going to come up on the test. So let's do one of those. I don't think I did this one in any of the videos. So the series 1 to infinity, n factorial over 100 to the power n. So get in the habit, when you see factorial, think ratio test, okay? So it's not necessarily always going to be that way, but it's like 99% of the time going to be ratio test, all right? And again, that it might not be convergent, but it should be a ratio test problem. All right, so let's try ratio test. I need an plus 1 over an. I'll do some root test problems after this. All right, so what is that? N plus 1 factorial over 100 to the n plus 1. Okay, dividing by an means multiplying by the reciprocal. So 100 to the n over n factorial. Next step, simplifying. All right, so I want to get the factorials over each other and the powers over each other. Let's see. So when I simplify the factorials, you know, hopefully you guys are comfortable with that. That's going to simplify as just n plus 1 over 1. Okay, anybody unclear on how that works? Okay. And then 100 to n over 100 n plus 1, that simplifies as 100, just 1 over 100. All right. And now, okay, so this is an plus 1 over an, and now I need to consider the limit as n goes to infinity of that. Okay. So this limit is going to be this limit, n plus the limit of n plus 1 over 100. Well, what happens as n gets really big? Limit's equal to infinity, right? All right, so what does ratio test tell me? So it tells me my series is divergent. So I would say n factorial over 100 divergent by ratio test. All right. Any questions? Apparently there is a limit on the number of slides I can have. 20 is apparently the max. I'll go back to the beginning and kind of erase over some stuff. All right. Let's do a root test problem. Okay, so this is my series. Since I got these big parentheses, everything's to a power of n, you know, multiple of n, in this case 5n, that is my hint that I need to do root test. All right, so I do root tests. Let's see, I need to first indicate what absolute value of an is, right? So if n is even, okay, see, if n is even, I'm going to have negative 2n to the power of an even power. It's going to be a positive number, right? That negative sign is going to disappear. And then I take the absolute value, cancels out the negative. What I'm trying to say is when I take the absolute values, the only thing that's going to change is that negative sign is going to disappear, right? So I take absolute value of an, and I'll just rewrite that to keep track of what it is. Okay, so absolute value of the an is just 2n over n plus 1 to the 5n. Okay, and then I take the nth root of absolute value of an. And what's going to happen? The n and the nth root are going to cancel, and I'll be left with 2n over n plus 1 to the power 5. Okay, and then I take the limit of that. And maybe this is where a little kind of insight is needed. It's not a hard limit. Think about what this limit would be. We could break it up by numerator and denominator if we want. Okay, if I take the 5th power of this, okay, what's the largest term I would have, the largest power term I would have in the numerator? It'd be 2 to the 5th, n to the 5th, right? Okay, so that's like 1632 n to the 5th, plus some other stuff, right? But all the other stuff would have smaller powers of n. Okay, I'm just rewriting limit there. And then what would be the largest power on bottom? It would just be n to the 5th, 1 n to the 5th, plus some other stuff, right? Okay, so I got same power on top and bottom. What's the limit of this? The limit is equal to 32. Okay, so limit's 32, which is definitely greater than 1. So what does root test tell me? Divergent. So I would say, to conclude, I would say an divergent. By root test. All right. Any questions? Okay. I'll go to 7:30. You guys, some of you have dropped out already. Leave whenever you want, and then I'll cut off at 7:30. And if you guys want me to cover anything in tomorrow's session in particular, just message me on here before the end, or email me later if you want, or web course message, whatever. Just for the sake of kind of completeness, let's do some other problems. Integral test. The only thing I have to say about integral test, about when you should use integral test, is look at your series. And this is more about deciding what test to use in general. Okay, so let's say you're given a series before you even get any kind of preconceptions about what you should use. Look at the stuff inside the series and just take note of all the features. Like, is there an alternating term? Is there a factorial? Is there everything to the power of n? And one of those questions should be, if it was an integral, could I integrate it? So maybe can integrate. Okay. And if the question is yes, then try integral test, because integral test is good because it tells you whether something's convergent and it tells you whether something's divergent. A lot of the tests, some of the, like half the tests, maybe it'll only tell you one or the other. Like maybe some tests you can use to tell if something's convergent, but then maybe the test is inconclusive if you meet other conditions. So the integral test is good because it's pretty clear cut. If you can do the integral, whether the series is convergent or divergent. All right, so it gives you both sides. All right. So I look at this series, and especially when I have like e's and ln's and stuff, that's usually, I usually think ratio test, root test, integral test, really. Because like when I have weird stuff in the series like e's and ln's, that usually means I'm going to do like ratio test or integral test usually. Okay, so when I see something like this, I first think, okay, ratio test, no, probably not, you know, but then I look at it a bit closer and I say, hey, if this was an integral, I could integrate that. I know it's a U-substitution integral. Okay, so I go straight to integral test. Okay, so what do? I set it up as my improper integral. Okay, and I rewrite with x's instead of n's. Okay, all right, so I write as the improper integral, then I rewrite as the limit. This is important. Okay, now the rest is just integrating. So I do my U substitution. I need a U substitution to integrate, right? I say U equals x cubed. And I think I did this in the video last night, but we can do it again. Du equals 3x squared. So du over 3x squared equals dx. Okay, so I'm going to plug all that stuff in. If you don't want to change your bounds, you know, just kind of leave blanks for the bounds. So what's going to cancel? The x squared is going to cancel when I do this U substitution, right? But I should be left with a 1/3 e to the negative u du. Okay. Let's go to a new page now. I can bring that 1/3 outside the integral. Well, it's e to the negative u. Yeah, there we go. All right, I integrate this. I can get a negative sign. Okay, I undo my substitution. And then I can use my original bounds. Then I plug in my bounds. So if I plug in 1, it's going to be e to the negative 1. Okay, so this is going to be, let's see, 1 over 3e minus this thing, right? Okay, so when I can just rewrite e to the negative x, or e to the negative t cubed as 1 over 3 e to the t cubed. Okay, now I can see this is a constant, and this limit's going to 0. Okay, so the limit of this thing is 1 over 3e. So this is a finite number, okay? So this is a convergent integral. So how do I wrap up? I would say integral convergent. So the series is convergent by integral test. Cool. Any questions? All right. Let's continue going. Let's kind of work our way back forward now. So we did integral tests, 11.4, comparison tests. Let's do a couple comparison test questions. Zach, no. So we find 2 types of sums: geometric series and telescoping series. And I might have said that before you came in. So after I upload the playback, because I talked about that a little bit, go back and watch the first, 5-10 minutes of this video. And I talk about that a little bit. So geometric series, and sometimes we got to play with the geometric series a little bit. So you got to be able to play with the geometric series a little bit. And telescoping series, if I give you a telescoping series, it's going to be pretty basic, no tricks. All right. So I favor the geometric series, and it should be that way on the final as well. But you should also know the telescoping series just in case. All right. So we're doing comparison tests. Okay. All right. Comparison test. How do I know it's a comparison test? Usually, comparison, especially if I have like polynomial over polynomial, that's a good indication it should be comparison test. This is not quite a polynomial, right? Because I got n to the 1/2. But really, let's see, I'll expand polynomial over polynomial to include like polynomial over powers of n and vice versa. Okay, so what do I have on top? I got a polynomial, right? It's very simple, n plus 1. And then on the bottom, I got n squared of n, which is just, if I can combine these into n to the 3/2, right? So basically what I have is n plus 1. Okay. So if I have something like that, I know I can do either comparison test, the direct comparison test, or the limit comparison test. So let's try that. Okay. So if I was going to compare this to something, what do I compare it to? I look at, I try and simplify this as much as possible. And maybe simplify is the bad word because I'm not canceling stuff, but I just kind of look at how could I make this, less complicated. If I got rid of the 1 on top, I would just have n over n to the 3/2, right? Okay. And then what is that now? This one, I could simplify. Let's see, that's 1 over n to the 1/2, right? Okay, then what's going on with this? This is divergent by p-test, right? Okay, so that means that, it doesn't definitely mean this is divergent, but that makes me think it's divergent. Okay, so which way do I need the inequality going? If I want to show this is divergent, I need to show this stuff's bigger than this stuff. Okay. So, and let's see, let's be careful because I need to check my 2 conditions, right? I'll call this my AN, and I'll use this one. Should I compare it to this or this? I'll stick with this. It's going to make the inequality easier. I'll call this my BN. I'll say AN's greater than or equal to 0 for all n greater than or equal to 1. Okay, BN is always greater than or equal to 0. Again, we could say for n greater than or equal to 1. All right. So that I checked that, and let's see, I need my inequality, right? Okay. Let's see, these are pretty much the same except I'm adding 1 on the top over here. So yeah, this has got to be bigger than that. Okay. All right, so now I got my 2 conditions for my comparison test. So let's wrap up. I would say n over n to the 3/2. So maybe I'll go ahead and say this is equal to, that is divergent by p-test. So my original series, n plus 1 over n square root of n, divergent by comparison test. Questions? Okay, keep going. I'll do a couple more of these because in my opinion, what I had hardest time with, I think, was comparison tests. I don't know, let me know how you guys feel, if you feel the same way. It's a little bit, I don't know, it takes a little bit of finesse, I guess. Another common time you'll see these is, or you'll use this, is with trig stuff. Okay, so this would be a good example. One plus cosine to the n, or cosine of n over e to the n. So trig stuff is another time when I use this, just because I have good bounds for trig stuff, right? I know trig stuff's always going to be greater than or equal to -1 and less than or equal to 1. Okay, let's see. So what do I know about this thing here? And we could actually do kind of like a squeeze theorem type thing. So let's see. What would I compare this to if I was going to compare it to something? Well, let's see, cosine of n over e to the n? No, because that'd be weird, because I would have alternate, the sign would be changing. It wouldn't be necessarily an alternating series, but it would go back and forth between negative and positive. What about the series 1 over e? Actually, I should use 2 over e to the n. Okay, what about this series? Well, this series is convergent, right? Because this is the same as series 2 times 1 over e to the n. Okay, so I could think of this as a geometric series with r equal to 1 over e, which would be less than 1. So this thing's going to be convergent. Okay, so that makes me think this thing might be convergent. So what do I need to do? I need to show that this thing's less than or equal to this. And I need to show everything's positive, right? Well, let's see. Cosine of n could be -1, but then I'm adding 1 to it. So this top's got to be greater than or equal to 0, and the bottom is always greater than or equal to 0. So I know, 1 plus cosine of n, that's always greater than or equal to 0. And what about this 2 over e to the n? Yeah, that's always greater than or equal to 0. All right, condition 2, I need an inequality. Well, cosine's always less than 1, so I can say 1 plus cosine of n. That's always less than or equal to 1 plus 1 over e to the n, right? Equals 2 over e to the n. And I don't have to write it, but I could write it as greater than or equal to 0 over e to the n. Okay, so this is really the important inequality here. I got this is less than or equal to this. Then I would say, to wrap up, I would say 2 over e to the n convergent by geometric series. Again, I'm abbreviating, don't abbreviate on the test. So our series is convergent by comparison test. Any questions on that? All right, last thing I'll say, what's the difference between comparison test and limit comparison test? Okay, so when should you use limit comparison test? If you try comparison test and you can't get the inequality going the right way, or you can't even tell what the inequality is, that's usually a clue to try limit comparison test. So I'll show you what I mean. Limit, and just as I don't want to tell you guys to avoid the comparison test, because comparison test is great. especially the higher you go in math, being able to work with those inequalities is really good. But limit comparison tests, I would say you could probably use it in more circumstances than the regular comparison test. So if you're ever kind of unsure of which to use, comparison or limit comparison, try limit comparison. So let's see an example of that real quick. How about this series? I'll kind of make one up. Let's say, okay. So let's look at this one and see what happens with this one. I try the comparison test. Let's try the comparison test. The regular comparison test, what would I compare it to? Okay, I'd probably try and compare this to n over n squared, which is equal to 1 over n, right? So I'm going to try and compare it to the harmonic series. Okay, but let's see, and let's, just to be safe, if n equals 1, I'd have 0 here. So just to be safe, let's start it at 2. That doesn't really change anything. Okay, I can still use the comparison test. All right, so what do I need to do? I need to check, is everything greater than or equal to 0? Yeah, for n greater than or equal to 2, that's greater than 0. 1 over n is greater than or equal to 0. All right, so that condition's fine. Now I need to set up an inequality, right? I know this is divergent. So that is telling me this is probably divergent, but what inequality do I need? I need this to show my original is divergent, right? So do I have that? Okay, let's look at the denominator first. I'm dividing by, so how does this compare with 1 over n? Okay, I'm dividing by a smaller number over here, right? So that would make me think, okay, I'm dividing by a smaller number, so this thing should be bigger, right? So it makes me think I have this inequality. But then look at the numerator. On top, oh, and let's see, instead of 1 over n, let's use the n over n squared. Okay, because then when I use this, it's a bit clearer how the inequality works. All right. So let's see, again, I'm dividing by a smaller number over here. That makes me think this side should be bigger. Okay, so it makes me think that. But then look at this, I have a smaller number on top over here. So that makes me think, well, no, wait a second, it should be less than or equal to. So the point is, I can't really tell what the inequality here is, right? It's not clear which one of these it is. So I can't, unless it's clear, I can't use the direct comparison test, all right? So when it's unclear, I think, okay, maybe I should switch to limit comparison test. Okay, so let's call these my ANs, and I could use either one of these for my BNs to be consistent. Let's use this. Okay, what does limit comparison test say? I need to do AN over BN, and I need to look at that limit. Okay, so what is AN over BN? Okay, that would be n cubed minus n squared over n cubed minus n. What did I do? I took this and divided it by this, and I skipped some steps and wrote the simplified version. Everybody good with that? Let me know if you're not. Okay, and then I need to look at the limit of this. Okay, so what's the limit of AN over BN? Well, I got n cubed over n cubed. That's all that matters, right? So the limit's equal to 1. So what does limit comparison test tell me? Okay, if I get a limit that's a positive number, okay, positive finite number, that means these two series are going to do the same thing, okay? So I would say, since limit AN over BN equals 1, and our series n over n squared equals 1 over n divergent, then n minus 1 over n squared minus 1 convergent by limit comparison test. And once again, don't abbreviate on the test, write out limit comparison test. All right, I will stop there for the night. I will do another session tomorrow, same time, 6 to 7. And if you guys want me to go over anything in particular tomorrow, email me, message me on web courses. You can tell me now if you like. And yeah, that'll be it. I'll be on here another couple minutes checking the names on the attendance thing. So if you have any questions, feel free to speak up or chat at me. I'll sign off when I'm done. No problem. Let's see.